Cool. So welcome to the second lecture. So last week we did an overview on memory management and went over the three classical algorithms, and then we did some mark sweep details, and we're going to finish that now. So we're going to finish mark sweep, and then we will do the main thing is compaction that will go this week. Okay. So remember, the garbage collection goal is to find which objects are reachable or unreachable from the roots. And then we want to reclaim all those that are unreachable. And the roots, we said this is kind of input we get from the language or from the compiler. So the roots can be, for Java, they could be local pointers, global pointers, all kinds of connections with other languages. We don't care. This is like an input to our world. We just get the roots from the compiler, from the language definition, from wherever. We know the roots in some manner. And what we have to do is determine which objects are unreachable from the roots. We consider them dead or reclaimable, and we need to reclaim them. This is the goal. Okay? And the general view is we have a heap that initially is all ready for allocation. We mark it blue. Then we start allocating, and eventually we allocate until the end of the heap. But some of the objects become unreachable, so they're dead. And the goal of the garbage collection is to identify them and make them blue again. So the allocator knows that these are places that can be allocated from. So this is the lifetime of the system, and it goes again. So from here, we'll allocate, it will become full, but other things may become white, and we'll do garbage collection again, and it will determine which can become reclaimable and reallocated. So this is the cycle. Okay, so mark sweep, we said we mark all objects that are reachable from the roots. We have some roots. They point to some objects in the heap. We follow these. We follow the pointers and the pointers inside the heap, and we see what's reachable. We mark it. Everything we encounter, we mark. And the things that are not marked are reclaimable. We go and reclaim them. So the marking phase is called marking. And the phase where we go over the heap and reclaim everything that's not marked is called sweep. So sweep, if you don't know, in Hebrew is letate. We sweep and so we sweep the heap, and we reclaim all objects that are unmarked. Okay. So we started with the standard engineering techniques. We'll do that almost only for this very simple algorithm. Usually we'll talk only about algorithms, but let's do this, speak a bit about engineering things, which are very important in the real world, of course. So first we said we avoid recursion because we don't know how deep the recursion will be, and it's dangerous to get a stuck overflow. Now let's talk about the bitmaps. So these are things that will help sweep. So where do we put the mark bit? And we could put it in each object has a header, so we could mark the object in its header. But this is not the best thing, and in order to see why, let's look at the alternative. So the alternative is to have a mark bit table apart from the heap on the side, like not inside the heap, but it will allow us to mark objects. How will that happen? So for each word of the heap, we'll keep one bit. That is an overhead of 1/64 to the space that we usually need. And so one bit for each word, and we will mark it if there is an object that we want to mark and starts at word 5. We will set the fifth bit in the mark bit table. Okay, so we'll just there will be correspondence between like the first word and the first bit, the second word in the heap and the second bit in the mark bit table. And we'll just, whenever there's an object that starts in the ith word in the heap, we'll set the ith a bit in the mark table in order to say that it is marked. Okay, so this will be like, instead of marking in the header of the objects, we will mark on a side table like that. And how do I know where to mark? If I'm on some word, I look at which word it is in the heap, and that's a word is 64-bit. So usually in a computer, normally in all the platforms that we know, an address is an address to a byte. So in each word, there are 8 bytes. And so we have like all objects starts in word limits, like alignment of words. So all objects, their address is divisible by 8, okay, because we only, the address is given by bytes. And so we always start in the beginning of a word. And so when the object starts, we can say that that is the location where we mark it in the mark bit table. So it's very easy to move from an address in the heap to the corresponding bit in the mark bit table. And it's very easy, if we have a bit in the mark bit table, to say which word in the heap is represents it. So we look at the distance, which bit it is in the mark bit table, and then it is that word in the heap that is marked as the beginning of a live object. Okay? If I have a bit here, it's clear which object starts here. There are no two objects in the same word. Each object starts in a new clean word. So this is a good way to mark. And why do I want to do this? It's so I want, during sweep, if I have this, I can go over this very small table. Instead of going over the entire heap, I go over something that is a lot smaller, which is much better in terms of locality. So I can go over large spaces, and then I find something that is actually marked and is alive, and then I have to go to the heap in order to find out what's its length and not reclaim that. But then I can go on over the side table, and I can go very fast and use smaller space in the memory in order to determine which is alive and which is dead. So this is good for sweep. I skip sequences of 0. I can do it very fast. And so the advantage is that this locality. I use a much smaller space in order to determine what's live and what's dead. Okay, questions about this? Okay, so this is the simplest maybe. The second thing is doing sweep lazily. So if you do sweep, you have a long pause where you go over all the objects and see which is alive and which is dead. And of course, also you have this locality issue that you go through a long array or the entire heap. So the idea was to break sweep into smaller segments of work. So I want to break sweep. So what do I do? This is an idea from from the 70s. So when I'm allocate, I'm going to not sweep. I'm going to mark, and then I'll let the program resume working. And when the program wants to allocate, it will look for a place where it can allocate from. How will it do that? It will just do the sweep. So whenever you want to allocate, you sweep through the heap or through the mark bit table or however you do the sweep, you sweep until you find free space to allocate from. And so until you find a long enough space to allocate from, you do the work of the sweep. You just release spaces. When you find a large enough space to allocate from, you just allocate, and then you stop sweeping. You don't sweep anymore. The next allocation will go on looking for its space, and it will go on sweeping. And therefore, sweep will be broken into like increments of works that will be done not at a single work unit, but as a segments of works that will continue while I'm allocating. Okay, so what's good about this? First, I have shorter pauses. I don't have this long pause for doing the sweep. So this is a good thing. The second thing is that it improves locality. Why does it improve locality? So anybody has, yeah, a question? Okay. Yeah, so what happens is maybe I have here, I don't know, this how to mark spaces that are free, but say I have this thing. Okay, I need to allocate something that does not fit here, but will fit here. Then what I do is I start to do the sweep. I tell the allocator, this is free. Okay, I tell the allocator, I have enough. Okay, no, this is free. And then I reach a space that is good for me, then I just allocate from it what I want. Or if I don't allocate it all, I tell the allocator this is free. And now the sweep pointer is pointing here, and the next allocation will start here. It will not start from the beginning. Right, because otherwise it will be a waste. Yeah. So correct. We need to keep like a sweep pointer that will go on sweeping, and the beginning will be you can use it for the next allocation after you finish the sweep. These spaces that have been freed but not allocated yet, you can use them for the next allocation. I could split to by sizes. Uh, Right. I mean, for anything you suggest, there will be an example that will foil it. People do things that are good for most benchmarks. Most benchmarks actually have small objects. So I don't know. In Java, I think the average object size is 24. So it's not like if you shoot for larger objects and medium-sized objects, you will gain a lot because there are not a lot of them. Usually it's arrays, and there are a few arrays that a program would use. But if you start shooting for that in building your algorithms of memory management, there will not be enough usually. Of course, you can build a program where it will be excellent or it will be terrible. But usually, if you try to, break it into sizes, in real allocator, they will say if I have a large object, I want to treat it separately because it doesn't fit very well the normal execution, and there are very few of them. So we'll talk about it. Yeah, I'll have like a limit, maybe half a K would be small objects. Beyond that, I will treat it differently. We'll talk about it a bit. Yeah. Yeah. Hash table. At the mark bit table? Okay. Yes. Yes. Okay, first of all, you can ask in Hebrew. If it's easier for you, feel free. So if I have this and I know that this is, here there is a bit. How do I know which object in the heap matches that bit? Yes, it's the corresponding word. That is where the object starts. If I look at the objects, I know its length, and then I know this should be retained. I should not reclaim it. Is that what you asked? Or? Okay. You want to now free it. Okay. Okay, so freeing it means, I mean, we're going to talk about allocator a lot, but what we said, we'll just use a very simplistic idea that you have a free list. So we want to free a space, you just add it to the free list, then it's free. I don't care about these bits when I allocate. Only for sweep, I care about this. But when I allocate, I go to the free list, I allocate from there. If I'm in the middle of doing sweep, incrementally, then I will go to this table and go on it. But I will not return to previous bit. I could clean them, I could not clean them. For the next collection, I will want it to be completely clean. So I may do it when I'm done with an area, just clean the bit here, or in the beginning of a collection, I could just go over the mark bit table and clean it, clear all the space there to 0. That's a decision you can make, but it's not used during allocation, just during sweep. More questions? Okay, good. So why do I have better locality? And I will stress throughout this course. I think this is not done in all the basic courses and in only when you go to systems courses or real courses that that work about real world computing, you will see these things about caches. The cache behavior and locality is very. If you want performance, you have to think if you can improve the locality of your program. If you do that, you may gain a lot of performance. So this is something that I'm going to stress throughout this course. So why do I get better locality when I do this? So anyone has an idea? Why is it good for locality? Okay. Okay, this is almost, yes. So you want to. Right, but this belongs to the previous slides where I'm either using bit table or not. But what I want to say here is, suppose I go through the sweep, I get to a place and I reclaim it. Now I also allocate it, so I let the program start working with it. So there is the memory manager came there and maybe suffered the cache miss, but now the program is going to start working on that and it's already in the cache. So the program is going to get cache hits. So this between the program and the memory manager, if the memory manager just goes over the entire heap, then everything that was in the cache is gone. And then when the program returns, it suffers a lot of cache misses. But if you go through some of the heap and then you let the program work on the same space that the memory manager works on, then they will cooperate on the same areas in the cache, in the memory, and then the cache will be warm. You'll have lots of cache hits. So if they both use the same space, it's very good. If each of them uses different spaces, your locality is not as good. So this is really good because when you get through the sweep to an area, you allocate it, and then the program starts to use it, then there is good matching between the GC work, the garbage collection work, the sweep, and the program. They're touching the same space. So this is good for locality. Questions about lazy sweeping? Okay, cool. Bitwise sweep is even more very, very useful in engineering. And here you're going to give up something in order to gain something else. And the idea is that usually you go over the mark bit table and you look for sequences of zeros between two ones. This is like free space. So you find the one, and then you look what it represents. So you have the heap, you have here the mark bit table, you find here a one, you find here a one. So you say, this one corresponds to an object. Let's look at its length. And then from here until the next one, this is the free space, right? And all of these are bits. You have to work with bits. And so you have a word with 64 bits. You're looking for the first bit in this. This takes some time, and then you look into the next bit if there is any other bit and so forth. all these bit work is taking time, and this method says let's not worry about all these bits. Let's give up small spaces. So what it says is I'm going to go over the mark bit table and I'm only going to look at full words of zeros. So if I have 64 bit of zeros, then it's very easy for me. I ask, mark bit table of I equals 0. I don't have to work with bits. I'm working with words like I usually do in a program. And if it's 0, then I will reclaim the space around it. So I will look for, all the zeros here until the first one, and I will look at all the zeros here until the first one. But I will not, if there is like a mark bit where there is one here and one here, and between them there is some space that represents a free space to reclaim, I just don't care. I don't reclaim these small spaces that require me to look at bits inside a word. Only if there is a complete word of 0 that I can really check in a very simple way, like I usually work without bits, without looking at specific bits, then I reclaim the space. Okay, so I give up some small holes. Like in the company where they worked on this, they call it black holes. They just did not reclaim them. But this is creates a very fast search for the next 0-bit sequence because it's just a word in this mark bit table. And a word represents 64 words that all have to be unused in order for me to find these 64 bits that are all zeros. Okay, and it has to be aligned. Is this clear what I'm gaining and what I'm losing? Yeah. Yes. If everything is like that I have like, maybe the first bit of each word is set, and there are free spaces, but they are small. They're less than 64 words, each of them, then I may not reclaim anything because of that. Yes. It doesn't happen in real world, and yeah, and no one defends against it. So you can ruin, you can work on Java and make it blow up space just because of that. Yes. Yeah. So I do when I find this word of zeros, I do go back and forth with bits playing and do the detailed work in order to really understand what's the space that I should give up. But each bit here is 64 bits. It's like a word. This is of the table. I take 64 bits of the table. I see there's 0. I go back and forth, and I see, maybe 88 bits of zeros. It implies 88 full words that are going to be reclaimed. So I'm keeping the alignment of a word. Yeah, exactly. Yes. This is like the mark bit table. No, it doesn't represent an object. There could be, a large object, and I just mark its beginning, and there could be a small object that I mark its beginning. Usually, an object is at least 2 words because there's a header. It could be small, it could be large. I just mark the beginning. Yeah. What? So I have here a one and here a one. I found. But I want to add to the free list an entire chunk of free space. In order to find that, I have to go to the previous one, see its length, and then go after that, after the previous object. And I have to go until the next object, and then I have a full area of space that I can free, and I can add it to the free list. Yeah. Yes, if there's an object with a few words, there's only one bit that's set in the first word that this object starts. Okay, yeah. Why not mark all the bits? So if you have, so it's simpler and shorter, right? If I suppose I'm marking an object and then I go and mark the bit, I could go starting to mark all the bits in the object. If it's a large array, it will be disastrous, right? If I have, a mega space of an array, I will have to mark all the bits inside. It will take me a long time, and in general, I have to, it's 5 words that I have to mark. Then I will have to. This is like bits games where I have to mark exactly the right bits inside a word of a mark bit table. It will take me more time, and I just prefer. I could do this, but it will be more costly. Yeah. No. I go for just words of the mark bit table aligned. Like this is the first bit. This is the 65th bit. If you start from 0, this is the 0 bit. This will be the 64th bit. And then I just go by words. I go to the next word, ask if it's 0. Maybe because of alignments, I will miss some objects, but I will always miss small spaces. Maybe you'll have an exercise that will, calculate this. Okay. Cool. Okay, we have bitwise sweep. So now we can finish mark sweep. So mark sweep is simple. It is there are very advanced versions that we will maybe talk about in terms of concurrency and parallelism, and they're used in real systems. We've seen various engineering tricks, and the only problem is that we have fragmentation. Things do not move like in copying, and so we need to take care to compact the heap once in a while. And this is our next topic. Okay, questions about mark sweep before I switch? Okay, cool. So we want to compact. When we want to compact, we assume we've done a mark. So there's like a mark sweep which marks the live object. We need the marking. In order to compact, we need to know who is alive. And then after we know who is alive, we move them. And during this lecture, we're only going to talk about compaction, like how we move them, which will turn out to be non-trivial if you want to do it efficiently. But we assume there was a marking phase before that, and we know which objects are live. This is assumed. You cannot, you need to know who is alive in order to compact all the live objects to the beginning. Okay? And I'm going to ignore it, but assume there was a marking phase. Okay, so compaction. We're the fragmentation is a big problem here, and we're going to talk a bit about the motivation, and then we have 5 algorithms that we're going to go through this lecture, and then there is one algorithm which is more advanced and includes parallelism and concurrency, which I want to delay to around the 10th lecture of this course, just because it's a bit more complicated, and this is the plan. Okay, so let's start with the motivation. So, of course, large objects cannot be allocated. This is the main thing. If you have like small fragments where you can allocate from, comes a large object, you want to allocate it. There is space, but not consecutively, so you cannot allocate this object. This is the main motivation, clearly. But there are other things. So locality is, as I said, important. I will say it again and again. What happens in real programs, as we see, is that you allocate stuff that relates to each other. So there's a new student coming to the Technion. I allocate, his personal details, his transcript so far, everything related to him. And when I ever come to look at this student, I'm going to look at more than one piece of this information. So if I allocate consecutively things that come next to each other in time, So I want to allocate 4 objects. If I allocate them one by the other, then it's going to be good for performance later in the execution because these objects are going to be touched together in time, also in the future. So this is like in normal program. This is what people found that is the right way to do. So if I manage to have a large space to allocate in, then it's good for locality. Okay. Okay. This is said here. Objects allocated together tend to be accessed together. The sweep is going to be longer if there are lots of small spaces that needs to be reclaimed and added to the free list, then it's more work for the sweep. If it's one long area to be swept, then it's going to be faster for the sweep. And allocation itself becomes difficult. So if you want to allocate some space for an object and there are all these small spaces that do not fit and eventually there is a large space enough for it, then it might take more time to find it. Okay, so we have motivation to do this. This is done in practice. And compaction algorithms, they compact usually all objects together. Sometimes there will be reasons to compact them in piles. So we'll not just have one pile in the beginning of the heap. Maybe we'll have several piles, but we'll talk about that later. So the generic task is we assume we've marked, we know what the live objects are, and now we want to move objects to one or small number of areas in the heap. And then this is very important to not miss. We have to modify the pointers in the heap. So if something moves and there is a pointer to it, I have to modify the pointer. And this is sometimes people don't notice it in the beginning, but this takes half of the time of the work for compaction. I have to completely change all the pointers in the heap. So we have to do these two, and we're going to start with the simplest algorithm, like 2 fingers it's called. It's very simple. It assumes that all the objects are of the same size, which was correct in Lisp. In Lisp, all objects were like, of size 2 words. And it was good then, it's not good now, but it's so simple and it's useful to understand this algorithm. It has 2 passes over the heap. We're going to count passes. This is going to be one of the things we're going to count as the efficiency of the algorithm. So we have 2 passes over the heap. The first pass is going to compact, and the second pass is going to update pointers. These are going to be the 2 passes. Okay, so here it is. I have these 2 fingers. One looks for free space in the beginning. The other looks for live space from the end. Okay, so if I look at these 2, the free space is already found. The live space, this guy has to come here in order to find the live space. Here it is. What do I do now? Switch, right. I take the live thing and I put it in the empty space. Since all objects are of the same size, it's always the case that in the free space I can put the live thing that I found. So I switch it and then I go on for the next free spot here and the next live spot here. Here I found it. And then I switch again. I put the live thing in the hole that I found here. And basically now I go on searching and these 2 fingers meet. When they meet, I know that I'm done with the first phase. I've compacted all the objects to the beginning. But now I have, I need to fix pointers. And what I do here, when I move an object, I keep a forwarding pointer. I tell myself where it was moved into. So 5 was moved into here. I keep here a pointer to where 5 was moved. 4 was moved into here. I keep here a pointer to here. And notice that all this space is going, it will not matter after I finish the compaction. It's going to be a free space and the program will not need it. So I can just put things there and I don't disrupt anything. So I put here forwarding pointers that tell me where the objects have moved, and I will use it for fixing the pointers of the heap. So when I compact, this is just saying in text what we described on the picture, so I'm going to go through it. But the next pass, we're going to go over all live objects, which means I'm going to go over all objects that I finished compacting to the left side. And for each pointer inside an object, I'm going to look where it's pointing. If it's pointing, inside this space, then it's fine. These things were not moved. Nothing was moved from this space. If it's outside this space, then I know that the objects they point to has moved. But I also know where it was moved. If I have a pointer pointing to here, I look at the forwarding pointer and it tells me where it moved so I can fix the pointer. So all I do is I go over here. If there is a pointer pointing here, I fix it with the forwarding pointer. Okay? So this is the fix pointers. Questions about this algorithm? It's the simplest. It works. It's conditioned on all objects being of the same size, but it works. If you want to adapt it to variable size objects, you could do maybe what was suggested here, to break the heap into different sizes of objects and do each of them separately. Like if I keep all the objects of a specific size together, I can compact inside this and inside this. So there's no point in discussing this too much because it's a bad algorithm. And so it will not be used in practice. Let me do the analysis first and then talk about what's bad about it. So the complexity is the number of heap passes in this algorithm. It's going to be 2. It's going to be very good. I don't have any auxiliary tables here, which I will have in the future, but right now, just 2 heap passes, no auxiliary tables, cache performance. And this is the most problematic thing here. What happens here is that I take objects that were allocated in the heap and I move it to arbitrary spaces, right? I found an object here and I move it here because this was full and this was empty. So I just move it. And it's just completely loses all the relationships. Like if objects were allocated together, one will go here, the other will go here. They will have no relation after the move. So this is going to be very bad in that sense. It's going to kill the locality of objects as they were allocated. It will change their order arbitrarily. And I can tell you that this thing is, we've tried to implement this algorithm with some modifications to make it work with variable size. We've tried to do it for Java, and it lost about 20% of the execution time, which is huge. Like just because locality was lost and the order of objects was messed up. So cache performance here is terrible. Extra space required in this algorithm, nothing. You just work within the heap. You move stuff, you keep a forwarding pointer in the heap, and you need no extra space. Restrictions on objects, you have here the equal size restriction, but there's no real point in extending this algorithm because it's just bad in locality. So we'll not talk about extending it. Compaction quality is this, the order, the objects in the output, which is not good here. It's arbitrary. And the number of packed areas here is excellent. All move to the left side of the heap and they are packed in the left side. So these are the things we'll consider in all of our algorithms. And in general, for object ordering, there will be like 3 things that could happen. What we've seen here is arbitrary. It depends, where I found an object and where I found a hole, which is quite arbitrary. And so so this is the worst, and this is not going to behave well. The best is the sliding. So we just move everything to the beginning. If this was how it was before the compaction, this is how it is after. The order of objects is maintained, they're just compacted to the left. So this is considered the best, just performs best in real life. And this is something else that we'll see next week when we do the copying garbage collection. It will be close to linearizing. What does it mean, linearizing? I go to the first one and I make it first, and then I look what it points to. So 1 points to 3, I put 3 after 1. And in normal execution, maybe I'll go to 1 and I'll check the pointer, and then I'll go into the object referenced by 1. And so it may be good for the execution. And so you see 3 comes after 1, and then I look what is referenced by 3. It's 4, so I put 4 after 3. And then 4 looks at 2, so 2 comes last. This is called linearizing. This is a very simple example. Normally, if I have 2 pointers coming out of 1, I'll have to decide which of them to put next to 1, and then what to do to go to the pointers that go out of that object, or bring the next thing that is pointed by 1. It's going to be a lot fuzzier. It's not going to be as nice as in this very simple example. But when we'll talk about copying collection, we'll think of it as linearizing. It will be close to this, and then it will behave okay. It will behave good. The best behavior will be if we just keep the order of objects as they were before the compaction. Okay? So these are the 3 possibilities. And arbitrary is what we had in the 2-finger algorithm, and that's terrible. So we don't want that. Cool. So 2-finger properties, it's very simple. It's relatively fast. You have 2 passes. And the second pass is only on live object, which is even better. But 2 passes, basically. You don't need any extra space, but the objects are restricted to equal size. And the order of objects in the output is arbitrary, which is terrible. So it significantly deteriorates the program performance. So no one will use it. Okay, so questions about the 2-finger algorithm? Okay, so let's break 10 minutes and meet at 30 to continue. אוקיי, אז אנחנו רוצים לעבור לאלגוריתם הבא. Yes. You should remind me, yes, but everyone is helping. Yes, cool. Okay, so I want to move to the next algorithm, which is going to be sliding. So what I'm going to do is still keep a forwarding pointer, and the forwarding pointer will say for each object where it moves. There will be no restriction on the size of the object. All sizes are possible. And I need to now move the object. What's the basic problem that we have here? Right. That's more. But if I want to design an algorithm like this, what's the first thing that I have as a problem, which someone asked me during the intermission? Okay, I will say the problem is that when you move it, you're going to kill the forwarding pointers, right? If I move this and put it in the beginning, then it's the same heap. It's just depicted in different locations, but this moves here, so this forwarding pointer is going to die, right? Because the third word of this object is going to be put here. And still, I'm going to have this information here, but if there is any pointer that points to this location, there'll be no way to know where it moved. So this is something we'll have to worry about. And so worrying about this creates 3 passes over the heap. Okay, this is going to be like this. So pass 1, I'm going to go over this and install forwarding pointers. And what would be the forwarding point? How do I know where an object moves? How do I know where this one moves? Where does it move? It moves to the beginning, yes. And this is because there's nothing before it, right? And so this moves to address 0. This moves to address 3. Why? Yes, because the size of the objects before it is 3. This would move to address 4 because the accumulated size of all live space before it is 4. And so when I go over the heap, I know where each object is moving. But if I'm here, I don't know where this one moves, right? I'm accumulating the size. Now I'm at the 13th object, and you ask me where the 7th object moves? I don't know. I only know the current object where it moves to. So what I'm doing is I'm going over the heap, and for each one that I see, I install a forwarding pointer to where it should go. And I know for each object that I meet where it should go because I just accumulate the live space before it. So I do this for all these objects. And now in the second pass, I'm going to modify all the pointers. So I'm going to go over each pointer that's in objects. I'm going to look where it's pointing. So maybe it's pointing to the green object, and then I know where it's moved, where it's moving. So there is a forwarding pointer. So if there is a pointer from, I don't know, here to the green object, I can here change it to be to the right location after the move, after the compaction. Okay, so I can fix all pointers in the heap to show the right location after compaction because I have forwarding pointers. So this is going to be the second pass. That's fine. And in the third pass, all I need to do is go again over the heap. Each object that I meet, I know where it needs to move, and I just move it. And then I'm done. Okay, this is also a simple algorithm, but I lose. I'm doing 3 passes instead of 2, and I need, like you said, an extra word per object in order to keep this forwarding address. Can I, merge each of these 2 passes? Can I do the first and the second together? What will happen if I try to, modify the pointer while I'm doing the first pass? Right. Okay. That's right. So if I have a pointer to an object farther in the heap, I don't know where it moves. I haven't gotten there, and there's no forwarding pointer there. So I cannot do the first and second passes together. Why can't I do the second and third? Why can I do the pointer modification and move? Yeah, no, I go over the heap. I see a pointer here, I fix it. I finish fixing all of this, I move it here. Then I go to the next. I fix everything here and I move it to where it. I'll do the second and third pass in a single pass. Yeah. Exactly. I could override it. If I move this to the beginning, I will not have this forwarding pointer anymore. I will have the third word written on the first word that initially had forwarding pointers. And now if I have a pointer from here to here, I don't know what to do with it. I don't know where it moved. So overriding these forwarding pointers, writing them with new data is killing the algorithm. It's not going to work well. So I cannot combine the first with the second. I cannot combine the second with the third. I need to do 3 passes. Okay? Questions about this algorithm? Cool. So properties, it's very simple. There's no constraint on object sizes, which is good. The order of objects is preserved. This, we said, is crucial to let the program operate fast. And the problem is 3 passes and extra space for the forwarding pointer. Okay, cool. So this is our second. So We had one that was bad because of arbitrary order. We had one that had 3 passes and extra word, and we want to do better than both, like try to get the best of both. So the next algorithm, Yonkers, we're going to get 2 passes and no extra space. We'll not need the extra word. And the order of objects is going to be preserved. And we'll see, I mean, this is part of, we'll see how it's done. Okay, so so I want to stress again that while I'm going over the heap, I only know where an object moves when I see it. I do not know where other objects move unless I keep some information. I could keep a table on the side saying, you know, the first object goes here, the second object goes here. If I don't keep information on the side, I only know where the current object moves. I don't know of any other objects. This will keep on coming and we'll have to deal with it. Okay, so, and also the relocation address is just the accumulated space before this object. These are 2 things to remember. So Yonker says, I cannot remember new locations for all objects. So what I'm going to do is I'm going for each object to keep a list of all pointers that reference it. Okay, so I'm going to, for say I have an object, I'm going to have a linked list from its header to all the pointer fields that reference it. When I get to this object, I know where it's moving. I'll go through the list and fix all these pointer fields to reference the new location. Okay, this is going to be the basic ideas, and I need to work with it. Now, if I have this linked list through the heap, I will not have extra space. I will have a linked list in the heap. I need to be careful about moving because I don't want to destroy these lists that will serve the compaction. Okay, so one thing that I will use is there is a header for each object, and this is correct for Java. And the size of the header is more than a pointer. It's either 1 word or 2. And there is a word here, I will have to assume this, that doesn't look like a pointer. So maybe, so a pointer points to a word, so it has 3 least bits, significant bits, 0, right? Because each word has 8 bytes, it's always that a pointer has 3 zeros in the least significant bits, because it points to a full word. Also, in systems that we have today, the most significant bit or 2 of them are zeros in the user space. So there are things that make a pointer look like a pointer. And there's also a pointer in the heap has to be within the limits of the beginning of the heap and the end of the heap. So I just need something in the header that does not look like a pointer. You'll see why I need it later, but I will need such a thing. Okay. And I will use this structure to thread pointers. So I'll do this linked list. So here is what I want to do. So suppose I have this object, and there are 3 pointers in the heap that point to it. And here they are in objects ABC. And I want to create a linked list from this header into these 3 fields. So I'll be able to find them later when I move the objects and I want to update these fields. So what I'm going to do is I'm going to do something that I call threading a field into the header. So the operation will be very simple. If I want to thread this into here, what I'm going to do, I'm going to let this point to it. And in here, I'm going to put the value that is currently here. So the orange thing is going to come here, and the pointer is going to point to here. Okay, I'm going to keep here a pointer to this field that is the reference to this object. So let me do that. Okay, I'm going to point to this and put the value in here. So this is the threading of this field. Now I'm going to do the same thing for the second pointer. This is a field that I want to thread. So I'm going to put this value here, which means that this is going to point to the previous field. And I'm going to let this point to here. Okay? I'm doing the same operation. I'm letting this point to this threaded field, and I'm going to let this keep what's in here, which means that it will point to here. Let's do that. So here it is. I've threaded the second thing, second pointer field. Now I have a third pointer field that I want to thread, and I'm doing the same thing. I'm taking the value that's here, that's pointing to this, and I put it here. So this is going to point to this field, and I'm letting this point to what I'm threading. So this is how it's going to look in the end. And now it's great. I have, when I'm going to move this object, I have threaded all the pointer fields that reference it. So if I'm moving it to a new location, I can go through these fields and put the new location in here and put this back into the header. This is going to be how I will fix all the pointers. And it's important to me that this will not look like a heap pointer, because if it looks like a heap pointer, I will not know that the list ended. So the fact that this doesn't look, the thing from the header doesn't look like a pointer allows me to see that the list ended here. Okay, so this is the way I am going to work, and we're going to say thread p like a pointer. I'm going to thread a pointer means I put into p the content of the header, and I let the header point to p, like we did before. This is threading of a pointer. I'm going to thread pointers to objects in this manner, and eventually I'm going to have a list of all locations that I need to change. Okay, so I need to be very careful when I have a threaded list like that. I need to be very careful not to move objects that contain parts of this list, because then I'm going to break the lists and kill this algorithm. So I need to be careful. Okay, so yeah, this is code. I'm going to leave it in the slides. I'm not going to go into it in the lectures. So let's start with the simplified versions. Okay, I'm going to have 3 passes. This is going to be simpler. And then I'll move into 2 passes. So 3 passes, I go over the heap once and I thread all the pointers. So now all the objects have a linked list of all pointers that reference them. Now I go to the, I go over the heap again, second pass, and I use these lists to fix all pointers to the object. So any object, I go and fix all the pointers to it. I know what they are because they're threaded to the header of that object. I know where the header moves because I'm going sequentially over all objects, so I know how much space is required before it. And then I fix all pointers, and then I unthread the. So I move the header back to the object so that it will be consistent. And then finally I go over the heap and I move the object. So I thread all the pointers, I fix all the pointers, and I move the object. Okay, this is okay. This makes sense. Questions?
What happens if one object is referencing multiple other objects? Don't we, during the threading, get like some?
So I'm threading a pointer field. So for example, if I have this object pointing this object and pointing that object, okay, then what is going to be, this is going to point here, and you know, this may be the end, and this is going to point here. And that may be the end or continuing, but it's just fields, it's not the object. Okay, yeah. Find which step? To the header, yes. when I'm threading, I'm reversing the order, right? This is the end view. So from the header, you can go to all these fields and change them. Okay? You want to go back to the beginning? Let me go back to the beginning. Yes. Right, on D. We want to look at all pointers that look at D. I don't do it specifically for D. I do it for all over the heap. Okay, we will have an example for all objects in the heap, and that will make it easier. Here we focus on one object, but this is going to happen consecutively for all objects. Let me maybe answer this very shortly. If it works, then fine. If not, then the next example will help. If I have a heap, and I need to find all the pointers that look at the orange one. I go throughout the heap, and for each pointer that I see, I thread it to the object it points to. It means that I go over all the pointers in the heap, all of them. Each of them points to maybe different objects, but for each of them, I thread it to the object it points to. When I'm done with all the heaps, all the pointers and all the objects are threaded. Like this blue thing has all the pointers that point to it threaded to it. If it helps, then excellent. Okay, for you it's okay. But if it didn't help, then we'll see an example later. Okay, but so let's look some observations to make it a two-pass. So first let's give it names, forwards and backwards pointers. So I have pointers that go farther to higher location in the heap, like to the right, the larger addresses. And I have pointers that go back, like this one. They go to lower addresses in the heap. I'm going to call these forwards pointers and backwards pointers. Pointers that look forward and pointers that look backwards. Okay, I'm going to name them and I'm going to say things about them. So when I go over objects in the heap, I thread all the pointers that I see and I arrive at an object. I know that all forwards pointers to this object have already been threaded to the objects. Because if they're forwards, I've seen them. If they're backwards, I haven't seen them yet when I arrive at the object. But all the forwards pointers I've seen, they point from low addresses to higher addresses. And when I arrive here, all the lower addresses I've already scanned. And so all of these pointers that are forwards are already threaded into the header. Agreed? Okay. So if once we arrive at the object, we have all forwards pointers threaded into an object, and I know where it's going to go because I've arrived at it. I know how many words were occupied before that. So I know where it goes. I can go and fix all forwards pointers that are threaded into it. I don't really mind that it's forwards pointers. It's just for us that we understand what's happening. When I arrive at an object, I can fix everything that's threaded to it. All the pointer fields that I've threaded into it, I can fix. I know where it goes, and I know these fields that are pointing to it, I can fix them. But if I analyze it, these pointers are exactly the forwards pointers because what I've seen pointing to this guy when I've looked at lower addresses are pointers that go from lower to higher addresses. So analysis says that I'm fixing forwards pointers, and from the point of view of the algorithm, I just fix all the pointers that are threaded into this object. Okay, so this is what I'm going to do. I'm going to update pointers when I get to an object. It's not going to be all the pointers that point to it. I have not yet seen the pointers from higher addresses which go backwards into this object. But all the pointers that go forwards into this object, I've already threaded and I can now fix when I see it in the first time. And the second observation is when I'm done going over the entire heap in the first pass, I have all pointers threaded to it. And since I've already handled the forwards pointers, what I have is only backwards pointers. So when I come here, I know that each object has a threaded list of all backwards pointers that point to it. So if this is like a backwards pointer, it's going to remain threaded to this when I finish the first pass. I haven't handled it in the first pass. It's going to be threaded there. If there is a backwards pointers here, I know it will be threaded to here when I finish the first pass. Forwards pointers I've handled because forwards pointers, when I got to this and there was something that pointed to it, it was already threaded to it when I first saw it, and I fixed it, I handled it. I removed it from the thread, from the threaded list, and I fixed it to point to the new address of the orange object. So this is the observation. The forwards pointers can be handled at the first pass when I meet the objects the first time. Backwards pointers are guaranteed to be threaded to the objects when I finish the first pass. So this is what happens when I finish the first pass. All the forwards pointers have been fixed. All the backwards pointers are threaded. This is the observations. Now I do the second pass and I just see an object. I go and fix all the pointers that are threaded to it. And these are all the backwards pointers that are threaded to it. And then I move the object. And I'll have to show you that I don't destroy any, when I move it, it is not involved in any list. So I don't destroy lists. I will have to show you at the end. But I want the algorithm to be clear. So, and one thing that I want you to notice, there's a forwards pointer and a forwarding pointer. In the previous algorithms, I talked about forwarding pointers, which are pointers left to show where an object moved. So in the old location of the objects, I kept a pointer to show myself where the object was moved. This is not done in this algorithm. I don't use forwarding pointers. I do discuss forwards pointers, which is just a property of the pointer. It says that it points to a higher address from where it is located. Okay? So here we only have forwards pointers and backwards pointers if the pointer points to higher addresses or to lower addresses. Okay, so let's do some examples. So let's look from point of view. So when I go through the heap, let's look from the point of view of a specific object P. I'm going through the heap and I'm threading pointers. So what happens when I get to P, I know that these two, there are forwards pointers, they are pointing forwards. They're going to be threaded into P when I reach P. This is the situation. And now what I can do when I reach P in the first time, I know where it's going to move. I can fix these two fields that reference phi. So, P. So I'm going to fix them, and then I'm going to continue looking at the heap. Okay, so after the first pass, so when I reach it, I've handled the forwards pointers to it. I'm going to continue now the first pass, and at the end of the first pass, the backward pointer are going to be threaded into P. So let's look at how this looks. So P is going to have a thread that goes through the two fields that have backwards pointers into it. When I finish the pass, the first pass, I've handled the forwards pointers to P, and I have a list of backwards pointers to P that I need to handle. They're threaded into the head of P. So now I do the second pass, and when I reach P, I first handle these two pointers and make them point to the new location of P prime somewhere, and then I can move P to its location. And I will claim that when I move it, it will not be involved in any threaded list, so it's okay to move it. Yeah.
Can you explain again how you thread the backwards pointers?
I start by just going over the heap and threading everything that I see. I will do it not only to P, but now I'm focusing on how P looks, how it looks in the where P is a focus. Okay, so when I move, I thread pointers, and until I reach P, I see all forwards pointers to it. So they're threaded into it, and I can fix it when I get to P. I know where it moves. I fix them. Now I go on in the heap, and I go on and I thread all the pointers that I see. That's what I do all the time. I do in one pass, just thread all the pointers to their objects. Specifically, these two pointers that I will go through, I will thread into P, right? And it will look like that.
Okay, because that was the first one you saw, and then you threaded them. Okay.
Yeah. Backwards pointers have this property that I first see the object and then I see them. So all the forwards pointers I can fix while I see the object the first time. The backwards pointers will remain there threaded after the first pass. Okay. Okay. I'm. So this is the algorithm in. This is the algorithm as it is, and then I will do another example. Okay. So what is it? It's like in the first heap pass for each object P, I determine where O should move. I can do this in each pass. I just accumulate the space before it, and then I know where it's supposed to move. And then I update all the pointers that are threaded to its header. These are locations that point to it that I've already seen. This is forwards pointers. So I uh, update all these pointers, and then I look at all the pointers of O, like O's pointers, and this is outgoing. They could be going back, they could be going forwards, backwards. I don't mind. I thread all them, each of them, to the object that they point to, the reference. Okay, so this is the first pass. And I can analyze and say that all forwards pointers to O have been handled, and all backwards pointers to O have been threaded to it, but not yet handled. Now I do a second pass. For each object, I first determine where it should go, and that's because I just accumulate the space before it. And then I update all the pointers that are threaded to O, which now I know are the backwards pointers, right? All the backward pointers are now threaded to O. I go to them and I fix them, and then I move the object. Okay, this is the algorithm. Let's do another example. So we have this heap with 4 objects and some pointers. And suppose we're currently looking at this. We're currently looking at this object, the orange object. And there is another pointer that tells us where it moves. So each time I'm adding an object, I give it space, and that's the place where I'll move the next object. Currently, suppose I need to move the orange object to here. This is the accumulated space before it. I mean, maybe there's more objects there and there. I don't mind. But this is where I should move the orange object. I know it doesn't seem correct in this picture, but suppose this is where it should move. Now, what do I do? So in the first pass, I'm getting to it, and I'm looking at all the pointers that were looking at it, that were threaded to it. These are forwards pointers. These are these two fields pointed to the orange objects. That this is what I understand from the fact that they're threaded to it, and I fix them. So I need to put here and here this address. This is where the orange object will move to. And I need to put it here and here, and then return the header into the object to make it consistent. So I update, so I do that. You know, these two fields now point to where the orange object is going to move. And then the next step, and I return the header to its place. And now I move the free to leave space for the orange one, and then I will know where the red is moving. So I move it here. This is where the red will be moved to. And step 3, I thread all of the outgoing pointers to the objects that they point to. So this field should be threaded to the green one, and this field should be threaded to the red one. So How do I thread it? I have to put here the H, the green H, and I have to point to this field from that location. Here I've done it. I've put here the green H, and this now points to this field. Okay, so now, and I've done this simultaneously. So this pointed to the red one. I've moved the content of the red one to here, and I've let it point to this field. So I've threaded the two pointers that went out of the orange object. Okay, and now I'm going, this was the third step. Now I'm going to move to the next object. So I'm going to look for the next object and see that it's the red one. So I'm going to handle the red one. And now what do I do first? I first update all the threads that are threaded to the red one. I'm in the first pass. So I have all forwards pointers threaded to it. This is only this pointer, and I just change it to point to here, because this is where the red is going to go. So let's do it. It points to here, and the header goes back to the red. Okay, so I did the first step. Now let's do the second step. I'm going to advance the free pointer to show, to leave space for the red. And then maybe the next one will come. There's no next here, but I forward that. And the third step is going to thread the outgoing pointer of the red one. And this means that I'm going to take whatever is here and put it instead of the pointer. And whatever is here is pointing to this. So I need to put a pointer to here in the red one, and also point from here to this field. This is like threading of this pointer. So let me do this. So you see the green one now points to this as a threaded field. And this keeps what was in the green header before. Okay, so now I go to step 4. I try to move to the next object. I see that it's the end of the heap. I move to the second pass. Okay, so the second pass, I have to start with the green, and I'll do a bit of the green and then stop this example. So I go to the green one, which is first, and the first thing, I update the pointers that are threaded to the green. These are backwards pointers that pointed to the green and have to be fixed to the place where it should move. So if I go, I have this pointer and this pointer and this pointer that should point to the beginning. Let me do this. And I return the header to the green one to make it consistent. And then I move it. So this is the step 2 of this pass. I move this object and I'm done with it. Okay? And you can see that it's not involved in currently in any list, but I'll have to show that it's not involved. I'm not breaking any list by moving it. That's the example. Any questions? Yeah.
לפי מה במעבר השני יש לך בעצם את כל הפוינטרים האלה של האובייקטים שמקפיאים בעצם לאיזשהו מיקום, בעצם הפוינטרים
קדימה, ניק.
מצביעים מיקום שאליו האובייקט אמור לעבור. אז איך אתה יודע איזה אחד מהאובייקטים אמור לעבור שם? כי בעצם איבדת לתחקיר של אובייקט באיזשהו אופן, לא?
What? I have point. You mean when I'm threading outgoing pointers, or when I'm fixing pointers that are already threaded? I finished the first pass. Yes, I'm going back to the first object in the second pass, and then
נגיד סיימת להזיז אותו, עכשיו אתה מגיע לכחול.
I moved it. Okay, I moved to the.
נכון, עכשיו יש לך את רגע.
Okay, he's not pointed by anybody, but if he was pointed by anybody backwards, then I would have here a list of all the pointers that point backwards into it, and I would go and fix them. That would be fine. I'm not threading anymore in the second stage. I'm just fixing and moving each of them. That's okay? Okay. More questions? Okay. Okay, so this was the. So I want to claim that when I move objects in the second pass, they're not involved in a threaded list, because if they are involved, I break the consistency of that list. So this is the claim. When I'm moving an object in the second phase, none of its fields are part of the threaded list. So the first thing I should check that its header is not involved in a threaded list. And that's clear because when I go to this object, I start by looking at the header, going through all the linked fields, fixing them, and clearing the header. So the header is not involved when I come to move this object. So what I worry now is that maybe, outgoing pointers of this object made it be involved in threaded lists of other objects that it pointed to. So let's see. If there are forwards pointers from it to other objects that are ahead of it, then I know it's not in their list because in the first pass, I finished with all forwards pointers. So if there were forwards pointers and it became involved in lists because of that, that was cleared in the first pass. There's nothing that can happen there. If it has backwards pointers, then it gets threaded in the end of the first pass to these objects, and maybe it's still connected to them in the second pass. But if it's threaded to objects that are backwards, then in the second pass, I've already passed through these objects. It's backwards pointers. So I've seen these are like lower addresses that I go through before I arrive at that object. And so these objects were handled in the second pass, meaning that I looked at the threaded list in the header of these objects. I fixed all the pointers and I brought back the header. There's no list anymore from these lower addresses objects. So all backwards pointers cannot be in a list right now. These are objects that I already handled in the second pass. So no forwards pointers make this object be in a linked list. No backwards pointers make this object be in a linked list, and its header is cleared. So when I move it, I know it's fine to move it, and I break no list. Questions? Okay, so this is the Yonker. I'm going to leave code on the slides, but I'm not going to teach it. The properties, notice that all these threaded lists go through the heap. There's no extra space that you need. They go through the objects that are actually in the heap. So this is good for space overhead. I could do with variable size objects. This is also good. I preserve the order, so it's a sliding order. Everything moves in order to the beginning of the heap. This is great, and there are two passes, which is also good. Maybe you want to object to the two passes. This is, so maybe it's written here, yes, okay. So each pass is not like I'm going over the object and looking only at the object. Whenever I go to an object, I start looking at all the kinds of other objects because I thread it, I fix a threaded list. So these passes are not really two passes, there are more. And I will talk a bit more about how much real time is going, how much time is going into it. And it requires a header that's distinguishable from a pointer, which usually we have, but there could be cases where we don't have, and then we have to do something else. So these are the two negatives here. The two passes are more complicated, and they're not just passes, and I need this constraint or restriction. Okay, so how many times is an object really touched? I'm saying two passes, but an object is not touched just twice. So it is touched once by the first pass and again second time by the second pass, But for each pointer that references it, this pointer is going to come and thread itself into the object. And so there is a touch of the object. We touch the object for each pointer that references it. And then for each pointer in the object that is threaded into another object, whenever I fix the list from the other object, I'm going to go to this object and change its pointer. So I'm going to touch it again. So for each outgoing or ingoing pointer to the object, I'm going to touch it. So I'm touching an object more than 2 times. I'm touching it several times during these 2 passes, which means that it's more expensive. Um, you could ask about asymptotic complexity, but all the algorithms have asymptotic complexity, linear in the size of the heap. So this doesn't really mean a lot. You have to compare these by just trying it on benchmarks. And the algorithm is not bad. It was used in actual systems for a while. And maybe I'm saying this. So, okay, so this is pointing out the ideas. If we have no space overhead, we cannot remember. So when we come to an object, we only know where it moves. We don't know where other objects move. So we have to stick to using the information of where it moves only when we see it. So the solution that they present here was to create this linked list that allow me, when I come to an object, I fix addresses that have pointers that point to it. I fix all these pointers and I know them because of this linked list. And this analysis that talks about forwards and backwards pointers allow me to do it in 2 passes and not 3, because I understand how these things go and I know that I can move it without foiling any threaded list. Okay, so these are the ideas. If I look at what we've seen so far, the 2-finger doesn't need space overhead. It's 2 passes, but the object size is fixed and it has an arbitrary order, which is terrible. Lisp2 needs a space overhead of a pointer per object. It has 3 passes and it can work with the variable size object and it's sliding, which is good. So it has a high cost but good properties. And the threaded one does not need any space overhead, which is great. It does 2 passes, but we've said there is a caveat that these passes are expensive. And it can work with variable objects and it's sliding. So generally, it has good properties. So I'm. Do you want me to continue or maybe stop a bit early? Will it disappoint you very much if I stop a bit early? Okay. No. Okay. So one question. Yes.
עדיף אתה אומר שזה דורש עוד מקום של פוינטר, ומתחיל לבדוק שבסוף לשניהם יש כאילו תוספת הזאת. אם בהדד אני יכולה לשים את זה בהדד, אז גם בלי.
So in the threaded, what I do with this object in the header, I move it, I keep it somewhere else, and then I bring it back. No, yeah, I don't know where it can point to a place where there's data that's space that is used by an object, so I cannot put it somewhere else. Yeah, good point. Okay, thank you. See you next week.